Hi everybody, and welcome to another edition of Existential Physics with Ogar Plinkleton. I'm Ogar Plinkleton, and today's video is one of my favorites. We're going to be calculating the friction between the sliding mass and the surface upon which it's sliding. And I really like this one because we're going to be calculating that friction using conservation of energy principles, straight line analysis, and lots of algebra. So let me show you exactly what we're going to be doing and how then we will be calculating the friction. Okay, here's our experimental table. This is the mass. It's a bunch of little masses taped into a slider, and on the bottom is balsa wood, and that's going to be sliding on the surface. So we're going to be calculating the frictional force between this balsa wood and the surface that it's sliding on. This is attached to a string, as you can see, and it goes over a frictionless wheel. On the other end of the string are more masses. Okay, and so when this is on, the mass that's hanging on the string is on the floor, we have a 0 point right here. And we're going to be pulling this back in 10 centimeter increments marked with these pieces of tape. And what I'm going to simply do is pull this back to the 10 centimeter mark. And when I pull that back 10 centimeters, and you'll be able to see this when I do the experiment, but the mass down there is now off of the floor by 10 centimeters. And I'm just going to pull this back and let it slide, and then I can measure the distance from the 0 mark to how far it slid. And I'm going to do that 5 times at 10 centimeters, 20 centimeters, 30 centimeters, and back here is 40 centimeters. And then I'll take the mean of each 5 of those, and that's what our data point will be. Now, some things to clarify. We're going to be measuring this friction, but we are ignoring the friction between a string and the wheel and the axis, any energy lost due to the sound, and also it's not going to be an instantaneous friction, but it will be the average friction of the distance that this slides. Also, let's see, I might have forgotten something. I don't think so, but as I said, we're ignoring the other frictions and losses of energy, but truly they are second and possibly third or fourth order compared to the friction between this mass and the table, which is what we're trying to find. All right, back here up at the board, what I've drawn here are the different states, the energy states of our experiment that we're going to be looking at. State 1 is the instant before we release mass A. Mass A is what's sliding on the table. Mass B is what's hanging at the end of the string. In state 1, nothing's moving. We haven't released the mass yet. So we're going to count for the energy in this state, and this state again is right before mass A is released. Then we're going to look at state 2 and account for its energy. This is the instant before mass B hits the ground. So A has traveled through the distance h, and it hasn't hit the ground exactly yet. It's the moment before. The energy in state 1 has to be equal to the energy in state 2, and that will allow us, when we put that equation up, we'll be able to solve in variable form what the velocity or the speed is of mass B right before it hits the ground. And that's what we want to look for between these two states. State 3 is the instant after B hits the ground. And we're going to count for the energy in that state. And then lastly, the final state 4 is after mass A is finished sliding across the table. Remember, it's hit the floor. This is going to continue to slide, and we're calling that distance S for slide distance. And the energy here has to be equal to the energy here. And those are the equations we're going to be working with. And then we'll use algebra, and we'll also plot, and then we'll use straight line analysis ultimately to find the frictional force between the surface of the table and the bottom of the mass that's sliding across it. Okay, let's look at the energy balance equations between state 1 and state 2. Okay, here's our general energy equation for state 1 and state 2. So we have the potential of energy of mass A in state 1. Again, A is the mass that's sliding across the table. we have the potential energy of mass B. B is the masses that are hanging at the end of the string, plus the kinetic energy of A, plus the kinetic energy of B. That's state one. This is, again, the general equations. I'll get specifics next. Then in state two, again, we have the potential energy of A, plus the potential energy of B, plus the kinetic energy of A, plus the kinetic energy of B, and then minus dk. And this is the important term. That's the term where all the energies lost or transferred from the kinetic and potential is accounted for. And that's the variable that we're going to be used to calculating our frictional force, because the frictional force is taking energy out of the system from both the kinetic, or basically it's a change in kinetic energy. And again, as I explained earlier, this term by itself accounts for all the energy losses. As I said, the friction between the string and the pulley, the axle of the pulley and the pulley, the sound when it hits, any of those energies are accounted for in here. But as I stated earlier, that's second, third, fourth order, and we're just going to disregard them because the frictional force between the surface and the mass is much, 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 much greater. So we're just going to look at that term as the energy due to friction. Okay, so that's the general equation. Now let's get to specifics. I filled in the variables here. So the potential energy of mass A is equal to its mass times gravity times the distance from the ground, mass, gravity, z, plus the potential energy of B, which is the mass of B times gravity times its distance from the ground. And in state one, nothing is moving. Remember, this is right before anything's released. So neither A or B have any kinetic energy, 0 and 0. In state two, the potential energy of A, it's still Z above the ground. That hasn't changed. So it's mgz. B now is just before it hits the ground, so it has no potential energy. Both of these are moving now, so they have kinetic energy. The kinetic energy of A is 1/2 times its mass times its velocity squared. The kinetic energy of B, again, this is just before it hits the ground, so it's moving, is 1/2 its mass times v squared. These v squareds are the same because this is coupled by the string, and so whatever velocity this is, or speed this is moving, this has got to be moving the same speed as well. And then we have our minus dk, which again is the energy due to friction. Excuse me. Okay, let's do the algebra, reduce this, and solve for v squared. Okay, so let's on both sides we have the same term, so we can subtract that from both sides. So ultimately what we're left with on the left side of our equation is that. On the right side of our equation, we have these three terms. We can factor out the 1/2 and the velocity squared out of these two. And then this dk term. So the dk term is equal to, it's the integral of the force due to friction dotted with a change in h. Okay, and it's a dot product because these two are vectors, but energy is a scalar, and this has the units of energy, so it's a dot product. A dot product is equal to the magnitude of F times the magnitude of H times the cosine of theta, and in this case is the angle between the two acting vectors. And so, if we look, friction is opposing motion here, so the friction is acting in that direction, which is negative. Okay, so represents mass A. The friction is acting on it in that direction. The change in its direction here is acting in this direction. And the angle between the two then is 180 degrees. The cosine of 180 degrees is -1. So this is equal to negative the frictional force times H. And we put that in up here. The negative of a negative is a positive, so this term becomes that now. And again, we're solving for v squared here. So let's subtract this from both sides. We'll multiply both sides by 2 to get rid of the 1/2. And over here we can actually factor out the h and multiply both sides by 2. So we'll factor out the h. And then we'll divide by MA plus MB. And that's what v squared is equal to. Okay, we're going to need v squared when we do the energy balance between states 3 and 4. Okay, let's do the energy balance now between state 3 and state 4. State 3 is the instant after mass B hits the ground, and state 4 is when everything has stopped moving. B has hit the ground, A has slid from the 0 mark to wherever it ends, and everything is stopped. Okay, so we have our basic energy balance equation here, and let's put in the specifics. Okay, let's look at state 3 here. We have the potential energy of A, which is the mass of A times gravity times the distance off the ground, z. The potential energy of B is already on the ground, so that's equal to 0. We have the kinetic energy of A. This is still moving at 1/2 the mass of A times v squared. This is the same v squared that we calculated between states 1 and 2. And we have no kinetic energy for B because this is after it's hit the ground and it's stopped. And lastly, state 4, we still have the potential energy of A being mass of A times gravity times the distance z. No potential energy for B. No kinetic energy for A because it stopped moving. No kinetic energy for B because it stopped moving. And then we have our frictional loss due to the friction between A and the surface as it goes through S. Okay, so on this side we have over here we have this is the same on both sides, so we can get rid of that. And we have this, and it's just equal to the minus dk. Okay, so we're left with this dk is again the integral of the frictional force dotted with the change in, this time, S. And this again is a dot product just like in the previous one. And so this is equal to the magnitude of F times S times the cosine of theta. Friction acting that way, change in direction acting this way, 180 degrees between them. The cosine of theta is -1. Negative of a negative, so this is equal to the frictional force times S. And that's what we're actually trying to find here. Okay, now we can substitute back in the v squared that we found with the energy balancing between states 1 and 2. And that is v squared is okay, we put v squared back in. That's all equal to the frictional force times S, and we wanted to solve for S, so we divide both sides by the frictional force, and that just goes down right here. Okay, so there is S. Now, I'm going to show you why that's important, but first I want to run the experiment, and then we'll see why we wanted to solve this for S. Okay, let's run the experiment. I started to fill in the data sheet, and I've already weighed the two masses, which you can see at the top, and our drop distances are 10, 20, 30, and 40. And we'll run a test, 5 drops at each one of those distances. Then I'll fill those in down here, 5 at each distance, take the mean, and then that will be our skid distance at each drop height. And then we're going to plot those. Okay, let's put this down here. And I'll do the first one. There's our 0 mark. And the first run at 10 centimeters. Okay, we're done with the experiment. I filled in the data sheet with all our data points, and now what I'm going to do is plot this, the distance, the drop distance versus the S distance. And I've actually written an Excel program that I can enter all of these numbers, get the mean of each set, and then plot that. And I'll show you that, and we'll do that, and then we'll get to the straight line analysis part of this, which is going to allow us to determine the frictional force between the bottom of this mass and the table. I'm at the computer now, and this little Excel program allows me to enter each trial in of the drop distance, and then the skid distance, the 5 trials, and it gives me the mean. And we're going to be plotting that mean, the slide distance mean, versus the drop distance. So I'm going to go ahead and enter these. In trial 1, the 10 centimeters. Our first data point is 2.3 and 1.7. Right, I finished entering the data, and as I was entering it, Excel built the plot for me, and you can see here's the data points, and it is somewhat linear, and also Excel calculates the slope of this line for me right there, and that's important too. It's 1.193, and that's the slope. And now we can use that slope and the equation for S and use straight line analysis and then solve for the frictional force. Now we will do the final step in this process, the straight line analysis used to calculate the frictional force. So we have our plot, and we also have our equation from the conservation of energy analysis. From our plot, this is simply the equation of a line. Y is equal to mx plus b, where y is the y variable, m is the slope, x is the x variable, and b is the y-intercept. In our case, s is the y variable. I just interchanged the word slope here for m so we don't get it confused with mass. And our x variable is h. The y-intercept is 0, because at 0, 0, zero drop height, there's 0 displacement. Okay, and that then, remember we saw for S using our conservation of energy equations, which gave us this. Okay, so this is our equation. Slope H is equal to this. All right, so what I've done here, the rest is all algebra. I've divided both sides by H, and that goes, and that goes. And I multiplied through the denominator. Okay, so that's gone, and it's now over here. Okay, so that's what we have. Then I'm adding this to both sides, which I've done here, and that just only leaves this on the right side. Then I'm going to factor out the frictional force here, which I've done. That's what we're trying to find, and it's that times all of this is equal to that, and then we just divide both sides by this quantity to get F by itself, and then this is the equation that we can use to calculate the frictional force. All right, so I just taken the equation that was down here, put it up here. Let's put in our values. Okay, mass A was 158 grams. The units of force are Newton, and the units of a Newton are kilogram meters per second squared. So we need everything in meters and kilograms. Okay, so this was 158 grams, so that's 0.158 kilograms. Mass B was 89 grams, or 0.089 kilograms. And acceleration due to gravity, we're going to be using 9.81 meters per second squared. Okay, and that's all over the slope, which was 0.1293, and that's unitless because it is centimeters over centimeters. Again, times the mass of A, plus the mass of B, plus the mass of A. Okay, let's make sure our units work here. On top we have kilograms square meters per second square. In the denominator we have kilograms. And so this is equal to kilograms meters per second square. And that's the unit of a Newton, so we know we have our units and all these correct. And let's just do the math here, and we'll find out what our frictional force was. Okay, plugging that into my calculator, I got an answer of 0.73 newtons. And that is the frictional force, the average frictional force between the sliding mass, the bottom of the sliding mass, and the surface of the table that it was sliding on. Okay, this has been a rather long video, but I hope it shows you the essence of how useful straight line analysis can be. And you can use it if you have a physical relationship that you can relate to a linear graph. And it's a very, very powerful tool. Okay, that's it for this edition of Existential Physics with Ogar Plinkleton, and I'll see you next time.